Hello, today's video covers Picard's method. So, the question is, what happens if we can't solve a differential equation? We've learned quite a few methods at this point, but what happens when we have a differential equation that we don't know how to solve? We can use Euler's method, which we haven't covered in this class, but you probably covered in Calc BC. Or now, what we're going to learn is Picard's method for approximation. So here's the idea. Let's consider that we have an initial value problem. Y prime is equal to some function in terms of x and y, and we have this initial condition. So what we're going to do is we will integrate with respect to x. So when we do, we'll get y of x is equal to some constant, add the integral from our initial condition to x, of f of t, y of t, dt. So then if we use that initial condition, y of x naught is equal to y naught, what that gives us is y of x naught is equal to c add x naught to x naught, f of t, y of t, dt. So of course, this is 0. So that tells us that c is equal to y naught, right? C is equal to y of x naught, which we know is y naught. So then we have that y of x is equal to y naught, the integral from x naught to x of f of t, y of t, dt. So this is the same as where we started. Then you will solve using the method of successive approximations. So suppose that y naught of x is a continuous function that represents a guess or an approximation. So then y1 of x will be y naught, the integral from x naught to x of f of t, y naught of t, dt. Then once we find y1, we're going to go to y2. So our y2 of x then is y naught. Add the integral from x naught to x of f of t, y1 of t, dt. And you keep going. And so we obtain a sequence of functions, y1 of x, y2 of x, y3 of x. We hope that each successive function is a better approximation of y of x. And so we end up with, like we said, this list of functions. So yn of x then could be written as y naught plus the integral from x naught to x of f of t, y of n minus 1 of t, dt. And our n is 1, 2, so on and so forth. It is common practice to choose your y naught to be your initial condition. Okay, so this is all very theoretical. Of course, it's going to be helpful to actually see what this looks like in an example. So we only have one example, and in the packet, there is more room on the next page so that you can write. So we're going to consider the initial value problem that we're given. Y of 0 is equal to 2. We're going to find y1, y2, y3, and y4. So we're going to use Picard's method. But first thing that you would probably consider when you looked at this, if we weren't going to use Picard's method, I want you to notice that this is separable. So we do know how to solve this equation, but let's pretend that we didn't. So returning to that yn of x that we wrote above, it's going to be y naught, add the integral from x naught to x of f of t, y of n minus 1 of t, dt. So first thing, of course, that we should probably find is what is f of t, y of n minus 1 of t. So using our equation, that's just y n minus 1 of t, subtract 1. So our yn of x then, y naught is this initial condition. So that is 2 add x naught is 0, so 0 to x of y of n minus 1 of t, subtract 1 dt. Okay, so if we start by finding y1, our y1 of x is going to be 2, the integral from 0 to x of y naught of t, subtract 1 dt. Well, this y naught was the value that we were given before. So that y naught is 2, so this is 2 subtract 1. So this will give us 2, the integral from 0 to x of 1 dt. So our y1 of x then is 2 add x. So this is an approximation for the solution to the initial value problem we were given. Now, if we find y2, y3, y4, each successive approximation that we find will be a better approximation to the solution. So going to the next page, our y2 of x then, again, is going to be 2 add the integral from 0 to x. And then remember, in here, it's f of t, y of n minus 1 of t. So we got our y1 of x to be 2 add x. And our initial value problem is y prime is equal to y. So we plug that 2 plus x in. So this will be 2 add t, subtract 1 dt. So this is 2, the integral from 0 to x of t add 1 dt. So that gives us then y2 of x is equal to 1/2 x squared add x add 2. Okay, so y3 of x then, similar idea, is going to be 2 add the integral from 0 to x. This time it'll be 1/2 t squared add t add 2 subtract 1. Again, because we're just going back to this y prime and this y. So this is our y value, plugging in, except this time this was our y. Plug it in, we have to subtract 1 dt. So this is 2 add the integral from 0 to x of 1/2 t squared add t add 1 dt. Okay, so then our y3 of x gives us 1/6 x cubed add 1/2 x squared add x add 2. Okay, and lastly, if we go to find y4 of x, it's going to be 2 add the integral from 0 to x of that 1/6 t cubed add 1/2 t squared add t add 2 subtract 1 dt, which gives us then y4 of x is equal to 1/24 x to the 4th add 1/6 x cubed add 1/2 x squared add x add 2. Okay, so that is the rest of this problem, but let's talk about what that actually means. Like, where is this actually leading us to? Well, it looks like there might be a pattern that is emerging. Maybe we can write this as a series. So if we start here, it looks like we can write yn of x is 2 add x add 1/2 x squared add 1/6 x cubed add 1/24 x to the 4th, and so on and so forth. Okay, so this is really 2 add x, and then I can write that 1/2 x squared as x squared over 2 factorial. That 1/6 is 3 factorial. That 24 is 4 factorial. So on and so forth. So that's really 1 add the series from k equals 0 to infinity of x to the k over k factorial. So then, again, I'm going to have to move some stuff. So then if we take the limit as n approaches infinity, so if we were to keep finding all of these successive approximations, what's happening? Well, hopefully you recognize that series. That's the series for e to the x. So our work above would suggest that 1 add e to the x might be our solution. That is the idea with these successive approximations. When you use Picard's method, you keep finding all of these series or all of these functions in the hopes that you will recognize the function. The functions, rather, that they make up a series. So if we return to our differential equation, we did talk about in the very beginning that this is separable. So let's solve it using separation. We have dy over y minus 1 is equal to dx. If we integrate, we get the natural log of y subtract 1 is equal to x add c. So that gives us y subtract 1 is equal to c2 e to the x. Using our initial condition, so our y of 0 is equal to 2, we get 2 minus 1 is equal to c2 e to the 0, so our c2 is 1. So finally, we get a solution of y is equal to e to the x add 1, which is exactly what we thought it might be. Okay, so that was the one example that we are going to do. Do some practice on your own, and I will see you next time.